Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. We were discussing about immiscible flow. In particular, we just briefly introduced this Buckley-Leverett formulation, where the porous medium is at interstitial saturation, and then the wetting phase would be injected into that porous medium, and we want to study how saturation changes, how the wetting and non-wetting phases, how they come out, how they are collected, how they at what rate they come out at the effluent. So what we did is, we had earlier we had discussed about relative permeability and two phase flow. The model that we have in mind, we have this funicular and channel mode by which the flow can take place, and what would be these this capillary pressure, surface tension, contact angle, other rock properties, and how they affect this relative permeability. We have already gotten some idea of this by now. So we were discussing, we in fact just briefly introduced in the last lecture this Buckley-Leverett formulation, where we said that if we have a porous plug encased in a core holder or encased in some kind of wrapping, so that the flow cannot take place through the side, flow can only take place unidirectionally through this in this direction, and this is at interstitial wetting phase saturation, and it is what is injected to this is flow, but this is only the wetting phase is injected. So it is at interstitial saturation. What that means is that if there is if interstitial saturation is 10%, that is, this is the limit, that means 0.1 is the limit, water can be, or wetting phase can be in this porous medium by a fraction of 0.1. So what that means is that rest 0.9 part of the void volume is occupied by non-wetting phase. So let us say oil. So 0.1 is the wetting phase and 0.9 is the non-wetting phase. So that was the case in this porous medium, in this porous plug, and then we are injecting wetting phase, which is water, at a rate, the total flow rate is Qt. So this is what we are injecting at the inlet here. So we said that if we pick up a differential length at a distance x from the inlet, if we pick up a differential length delta x, then if we can draw quickly a volumetric balance, we can do volumetric balance because all densities they are incompressible, wetting and non-wetting phase. So density is not density is constant. So we do a volumetric balance in the sense this Qt is the flow rate, total flow rate, and we have defined already the this Fw, which is a fractional flow function, and Fw is given by the volumetric flow ratio at any point. Say at any point we pick up this is the ratio Qw by Qt. So basically Qt is comprising of Qta is equal to Qw plus Qnw. So Qw is wetting phase, Qnw non-wetting phase. So that is being injected, so Qt is injected, and we at every grid we have some value of Qt. If I break this into 100 such grids or 1000 such grids over the length, then at every grid we will have some value of Qw, some value of Qnw. So sum of them would be Qt, and we will have some value of Sw, which is the wetting phase saturation, some value of Snw, which is non-wetting phase saturation. And once again, some Sw plus Snw has to be equal to 1. So, to start with, we assume that this entire core is having, let us say 0.1 is the waiting phase saturation and 0.9 is the non waiting phase saturation. So, that the sum becomes 1, that is the total void volume. So, now this is, there is a flow going in. So, we said that the volume of this differential element, I mean the void volume of this differential element, first of all the overall volume, if area of cross section is A, if this area is A, so then this A multiplied by the delta x, that gives me the volume of this particular section. Cross sectional area perpendicular to the screen is area A and this length is delta x. So, A delta x is the volume, this multiplied by the porosity phi. So, this gives me the void volume, and out of this void volume, how much was the saturation to there initially, let us say at some point of time the saturation is SW at time t, and at time t plus dt this saturation had become SW plus delta SW. That means over duration delta t the saturation increases by delta SW amount. So, that means once again the what is the amount of so this quantity defines what? A delta x is the volume multiplied by phi, that gives me the pore volume multiplied by the saturation of waiting phase. So, this gives me the volume of waiting phase in this differential element, and here this gives me what? SW plus delta SW and multiplied by A delta x into phi. This gives me the volume of this waiting phase after t plus delta t time. So, this is at t time, saturation was SW. This is at t plus delta t time. We are assuming that over delta t time the change in saturation was by the amount delta SW. So, it was SW, now it is SW plus delta SW. So, what is the change in volume of waiting phase in this case? Change in volume of waiting phase in this case would be A delta x is the total volume multiplied by phi. So, this term remains as it is and multiplied by delta SW, because change means this and this, their difference. So, SW and SW will cancel out, only you are left with delta SW. So, this is the change in volume of waiting phase in as far as this differential element is concerned. And why this change has taken place? First of all, this change has taken place because, or that is the only reason this change has taken place, because there is a flow in and there is a flow out, and this in minus out, they are different. This in minus out is different. So, how much is in? In was Q W at x multiplied by delta t. Q is the flow rate means meter cube per second into second. So, this gives me the meter cube of water that has gone from the inlet, and what has gone out is Q W at x plus delta x into delta t, that is the amount that is leaving from the right phase. So, we take the difference between these two. So, in minus out is equal to accumulation. So, in minus out is equal to accumulation. So, these two we have to link, okay. And moment we link these two, we say that we take out this delta t out and we take this delta t up here, and we take out delta x out, we take this delta x here, and further Q W, instead of Q W we replace this Q W by F W Q T, and Q T is a constant. So, F W is varying over length. So, F W into Q T, why? Because F W into Q T here is equal to QW. We know that is how the FW is defined. And similarly, here also we do the same thing. Here we write FW at x plus delta x into QT. So, now we take out this QT outside, and what will and if we insist for a limit delta x tending to 0 here, and on this side limit delta t tending to 0 here. So, then we end up with here del S W del t term and here del F W del x term. Okay. And that is exactly what we arrived at here in this material balance, that del S W del t at x is equal to minus q t by phi a del F W del x. Okay. On top of that, what we did, we have this F W is the ratio of the water flow rate divided by total flow rate, or wetting fraction flow rate divided by total flow rate, and that was written as K by mu for, or K R by mu, relative permeability, because base permeability K will cancel out. So, relative permeability of, so basically we are looking at the volumetric flux as per Darcy's law of wetting phase divided by volumetric flux of Darcy's law over the wetting phase and the non-wetting phase. So, K by K, so K and delta P by L, those were cancelled, and it is written as K R by mu wetting divided by K R by mu wetting plus K R by mu non-wetting. So, that is how F W is defined. So, next what is done here is, so this is there is some readjustment in this material balance in the form of this equation, and then this equation was integrated to find out, if we integrate this. So, del x del t at constant S W. So, x at S W is equal to this quantity. This is basically this t goes to that side. So, del F W del S W remains as it is, t goes there. So, dt goes there. So, when you integrate, this dt became t, and the one add some x 0 term stating that at t is equal to 0, x is equal to x 0. Now, what is the meaning of this x S W? What does this mean? So, let us first see what we have written here, and then I try to make some meaning out of this expression, because what exactly is the x? Is it position of the front? But then I do not think it is just the position of the front. So, we need to define what we mean by x carefully, because x within a with a subscript S W, it is not just any x. Okay. So, here we so let us see what we have written here. Assumed that at t is equal to 0, the water saturation in the entire porous media is uniform and equal to irreducible water saturation. This we already know. This we already know. In fact, this we already know, that if we, this was the porous medium we have, and this porous medium, this contained this wetting and non-wetting phase. Initially, the wetting phase was at SWI, irreducible water saturation. So, that is exactly what it says, that at t equal to 0, the water saturation in the entire porous media is uniform. So, everywhere it is SWI, because we cannot go below SWI by any means. So, this is uniform and equal to irreducible water saturation. All water saturations from SWI to 1 minus SOR are represented at x equal to x 0. So, we are assuming as if I have some packets. Now we started injecting water. So, when I started injecting wetting phase, when I started injecting wetting phase from this side, this is primarily 90% of the void space is non-wetting phase and 10% is wetting phase, and I am injecting the wetting phase. So, what could be the range of saturation possible here? The minimum saturation possible here is SWI, and maximum water saturation minimum would be SWI, you cannot go below that, and similarly the maximum possible saturation is 1 minus SNWR, SNWR, which is given here as SOR. This is same as SNWR, non-wetting residual, or here O stands for oil. So, SOR or SNWR. So, you have a limit between SWI and 1 minus SNWR. So, water saturation in this porous medium has to remain within this range. Okay. To start with at t equal to 0, everywhere it is SWI. When you start injecting wetting phase saturation, then at the inlet this saturation would be 1 minus SNWR. You cannot go anything beyond, because you have to leave SNWR, the residual saturation in the porous medium, even after 20 or 1000 pore volumes of 20 or 1000 pore volumes of wetting phase injection. Still there would be non-wetting phase remaining, and that amount, that saturation is SNWR. So, this is the limit within which the water saturation can be changed. So, what they are saying is that all these water saturations, I mean, I can put some numbers, I can put this SWI as 0.1, let us say, and SNWR as once again 0.1, let us say. I mean, it is generally 0.2, 0.25 like this, and at that range, let us say we assume 0.1 there and 0.1 there. So, that means, so 1 minus SNW, so 0.1 is basically SNWR. So, 1 minus SNWR would be 0.9. So, within this range the SW can vary. So, what it assumes is as if I have packets of saturations. I have packets of saturations, some belonging, some 0.1, some 0.2, some 0.3, some 0.5, 0.65, 0.75. So, all kinds of saturation packets are present here at the inlet. And now, since I am injecting from this side, these saturation packets are traveling. Okay. So, when we write dx or del x del t at SW, this term implies at what velocity that saturation packet SW, this is that constant SW. So, that particular SW will be traveling at this velocity. So, let us say I am focusing on a saturation packet which has saturation packet whose water saturation is 0.3752. So, 0.3752 would be traveling at a velocity which is given by this. So, but let us say we look at the right hand side. So, how would I get Qt is already known, that is the total flow rate that we are injecting, that is some meter cube per second is known. Porosity we know. To start with, what is the porosity of this medium? A, the cross sectional, overall cross sectional area, that is known, and del FW, del SW. So, somehow we have to find out what is del FW, del SW. Now, I have some hope there, because already we have written Fw as equal to, you may recall, Kr by mu for wetting phase divided by Kr by mu for wetting plus Kr by mu for non-wetting. So, and we know further these Kr, this case, so this is Kr wetting, this is Kr wetting, this is Kr non-wetting, mu is constant. Mu of wetting phase, if it is water, it is close to 1 centipoise, and one can figure that out. Similarly, if it is oil, oil has this viscosity which is known. So, this mu can be just directly plugged in, but Kr would be, we already saw Corey's relation, we already saw this Kr would be a function of saturation. In fact, we have already seen those plots of relative permeability versus saturation. We have found that if we look at Kr versus water saturation, then which one would be going down with increase in water saturation? Definitely this curve is KRO, because KRO will decrease with increase in water saturation, whereas KRW is expected to increase with increase in water saturation, because more part of the pathways will now be available, because more part of the pathways would be occupied by water. So, they will be that pathway would be available. So, relative permeability would be higher. So, now we have some expression, some empirical relation. We have KRO as a function of SW and KRW as a function of SW. We already know this. So, we can put those equations here and we can find out what is FW versus SW, what is the relation. So, FW is basically, FW is only the function of SW. So, then we have some way of finding out the FW as a function of SW. So, by using these relations, using these correlations. So, now suppose in fact one can draw a plot of FW versus SW. A plot can be drawn. A plot can be drawn which takes shape something like this, where this value of FW is 1.0, and this plot will start here from SWI and this will reach 1 at 1 minus SNWR or SOR. So, this again within this range FW will take a shape like this, where FW will vary from 0 at SWI, if everywhere it is SWI, and so I can expect that at SWI only the non-waiting phase will flow, waiting phase will be 0, the fraction of waiting phase will be 0 if the saturation is interstitial water saturation. So, this is 0, whereas if the saturation in the plug is 1 minus SOR, water saturation 1 minus SOR, or in other words the non-waiting phase saturation is at their limit there. So, then it would be only the non-waiting phase flow and no waiting phase. I mean, so there you have these, or rather it would be only waiting phase flow and no non-waiting phase flow. So, this is the limit. FW is between 0 to 1, and if you use these relative permeability curve, these correlations, one can come up with a curve for FW versus SW. And this curve, so this curve now at any point, let us say at this SW, I am interested to know what is del FW, del SW. That is very simple. I have to draw a tangent at this point and find the slope of this. So, that gives me this del FW, del SW. Okay. So, what does this equation mean in that case? This equation means that these packets, let us say this packet saturation we are looking at is, let us say 0.4137, that water saturation, and 0.4137 I want to know at what rate this is traveling, or over time t, how far this packet will travel over time t, or at what rate this will be traveling. So, if we want to know, so for that 0.4137 I will go up, find out which point we are looking at. At that location I have to draw a tangent, find out the slope, that slope gives me del FW, del SW. Okay. And we put this time, we put this del FW, del SW, all these, this is basically QT. So, QT is known, phi is known, A is known, and x0 we can assume to be 0, because at time t equal to 0 all saturation packets are near the inlet. So, now we can find out this saturation packet we are referring to 0.4137, how far that will travel over time t, because some saturation packets will travel far, some saturation packet, for example, if we look at saturation packet which is 0.9, this 0.9 would not travel anywhere, 0.9 would be almost here itself. Okay. Whereas, you will find 0.1, that is the lowest, that can travel all along, because already this entire porous medium to start with, this was the saturation, and in between some packet will travel up to this much, some packet will be this much, some will be this much. So, that is why you recall what was the curve we got? We got this type of curve, saturation SW as a function of distance, and this endpoint was 1 minus SNWR or SOR, the same thing. So, this is the limit, that is what the saturation would be at the face, that would be least traveled, whereas this would be SWI, that means this is at the interstitial water saturation. So, the front has come up to this point. So, this part is still at SWI, front has come up to this point. So, rest of it is all still SWI, and here this saturation packet, this has travelled up to this distance, this saturation packet, this has travelled up to this distance, whereas saturation packet which is further lower, it has travelled up to this distance. So, how far they have travelled over time t. So, this curve that we are referring to, this curve is frozen at a particular time. So, this curve is frozen at a particular time. So, now this at this time, how far the saturation front has travelled, how far the saturation front has travelled. So, each packet how far they have travelled, we can find this out. So, this is what is XSW. So, now if we could see how it has been articulated here, all water saturations from SWI to 1 minus SNWR or 1 minus SOR. I mean, NW is the non-meeting phase, O is the oil. I mean, they are used synonymously here. These are represented at x equal to x 0, which is inlet, or rather x equal to 0 for our purposes. And each saturation will advance into the system at a rate that is directly proportional to dFW dSW. Each saturation is travelling at a rate, this is the rate, right, del x del t, that is the speed at which each saturation packet is travelling, and that is proportional to del FW del SW. And how we get del FW del SW? We got this FW, this expression was there with us, and these FW expression there, we already have relative permeability curves. We have, I mean, empirical relation. If one wants, one can write these relative permeability as a function of surface tension, contact angle and other rock properties, that is also welcome. So, somehow you can find at the end you have to come up with some expression either or some kind of curve between FW and SW, and this curve will very much look like this, because I can see that FW has to be 0 when saturation is SWI, whereas when the saturation is at the other limit, FW has to be equal to 1. FW 1 means only waiting phase is flowing, no non-waiting phase. FW 0 means only non-waiting phase is flowing, no waiting phase. In fact, you can see when this saturation here is SWI, as saturation SWI, what is flowing here? Only the non-waiting phase, right? Waiting phase is retaining its own saturation, it is not changing. So, what you are producing at the outlet is non-waiting phase, you are injecting waiting phase, but producing non-waiting phase, because that is the case, you are operating, your point is here, FW equal to 0, whereas this entire place, when it would be all flooded, this you will be here at this point, and so it would be only producing water, because water will be flowing through the system and oil will be simply trapped inside the pore as residual saturation at that time, and at that time the saturation profile would be this. That is the final thing. I mean, after injecting 20, 30, 100 pore volumes of water, 100 pore volumes of waiting phase, this would be the saturation, and but still it is 1 minus SNWR, because SNWR you have to leave that little amount of oil inside the system as residual saturation. I will build on this further on this in our next lecture. So, this is all I have as far as this lecture module is concerned. Thank you very much.